The image of the lone genius at a chalkboard is a romantic one, but it is largely a relic of the past. In modern physics, the solitary eureka moment has been replaced by something much more complex. Sabrina Pasterski's career began far away from abstract equations. At age 12, she was working in a garage, grounding herself in a hands-on mechanical reality by building a functioning kit airplane from scratch. This project led her into the world of private aerospace, networking at airshows with the very people commercializing spaceflight. She was on a track that most aspiring engineers would spend a lifetime trying to join. But she noticed a pattern. The work in aerospace was increasingly focused on robotics and computer science, systematic, predictable applications of things we already understood. For Pasterski, solving known mechanical problems wasn't enough. She wanted to apply that same engineering rigor to the parts of reality that don't have a manual yet. Today, the search for a theory of quantum gravity involves an enormous canon of research, thousands of specialized papers pulling in infinite, often disconnected directions. Because the information is so fragmented, the work has shifted. It's no longer just about finding one new equation. It's an engineering challenge of associating these siloed data points into a single, functional structure. Traditional academic models often hinder this process. Many universities treat their physics departments like investment portfolios, hiring a few specialists in diverse fields to hedge their bets, rather than to build a unified program. This leaves researchers isolated in hyper-specific subfields, while the institution's primary attention and funding flow toward more immediate revenue drivers like biotech or software engineering. We are trying to solve the most systemic puzzle in the universe using an institutional model that is designed to keep its data points separate from one another. The Perimeter Institute operates as the structural alternative. It provides the specific infrastructure needed for theoretical physicists to actually collaborate, valuing the work of the theorist on the same level an experimental lab values its hardware. When you apply this integrated mindset to a physical problem, you find things like spin memory, a phenomenon that functions like a test case for how space and time actually behave. We know that when a gravitational wave ripples through space, it physically moves the objects in its path. Usually, we assume everything just returns to its original position once the wave passes. But the math shows a different result. Because of the conservation of angular momentum, the space itself remains permanently shifted. The wave leaves a subleading distortion in the geometry of the universe that doesn't go away. This permanent warp is a physical record, a piece of data etched into the fabric of space that we can potentially measure and analyze. Proving the existence of this memory didn't require inventing a new branch of mathematics. It required building a bridge between two existing but separate theoretical discoveries. Pasterski took a newly discovered soft theorem and demonstrated that it was mathematically identical to an established Ward identity. Locking these two disparate ideas together revealed something much larger, a brand new universal symmetry in the laws of physics. This moves the work out of the realm of pure abstraction and provides experimentalists with a specific, testable prediction for future observations. It shows that valuable progress can be made simply by engineering the connections between the insights we already have. The path forward in theoretical physics depends less on individual flashes of insight and more on the infrastructure of collaboration. There is a lingering cultural attitude in academia that views talent as something that either survives a struggle or fails, rather than a resource that needs to be actively supported and organized. Progress happens faster when researchers operate like connected nodes in a system, actively helping one another process the vast amounts of theoretical data we've already generated. Building an airplane is a mechanical challenge. Organizing the global effort to understand quantum gravity is a human engineering challenge. The most significant hurdle we face isn't just decoding the rules of the universe, it's building the collaborative framework that allows us to understand them together.